Hello, welcome to the course PH5 BO6 Electrodynamics 2. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. Today's class, we are going to discuss some of the topics from Chapter 7, Electrodynamics. Now, I appeal all the students to go through the previous 4 revision lectures because whatever I am going to discuss now onwards is an extension of what I covered in those revision lectures. The most fundamental law which governs current flow through a material is Ohm's law. I'm sure you all are familiar with it. Ohm's law says that voltage or a potential difference V equal to current flowing through a material I multiplied by resistance R. Now let's try to develop a more fundamental, a more generic perspective of Ohm's law using whatever electromagnetism we have learned so far. You know that to make a current flow through a material, you need to push the charges. If J is the current density and F is the force per unit charge, then current density is proportional to the force. You can replace the proportionality with a constant sigma known as conductivity, or the inverse of conductivity is known as resistivity. Now, conductivity tells you how fast the charges move in response to a given push. The unit of conductivity is Siemens per meter and the unit of resistivity is ohm meter. Now, for conductors, the conductivity is very high or resistivity is very low. It's around 10 to the power minus 8 ohm meters. For semiconductors, you have moderate values of conductivity and resistivity, and for insulators, resistivity is extremely high and conductivity is very low. So you can say for a perfect conductor, conductivity is infinity or resistivity is 0, and for a perfect insulator, conductivity is 0 and resistivity is infinity. Now the force which we are talking about here, it could be anything. It could be a chemical force or a mechanical force, but let's stick to a specific type of force, the electromagnetic force. Now in this case, the current density can be written as sigma multiplied by the electromagnetic force E plus V cross B. Now in the case of a current carrying wire, the velocity of charges is extremely low. So you can neglect this term and write J equal to sigma times E. This is the fundamental form of Ohm's law. Now when I said velocity is very negligible in the case of a current carrying wire, some of you might have raised your eyebrows, right? This is against our common sense because in our daily experience we find that moment we put on a circuit, the bulb glows instantly, or moment you switch on your electric geyser, it starts heating up instantaneously, right? So we tend to think that the electrons in the circuit is moving very fast. That's why we see an instant response. But I said here velocity is very low. Now I don't want to leave anything to your assumption or imagination. Let's do a quick estimate, a quantitative estimate of velocity of charges in a circuit, and that makes things clear to you. So let's answer this problem. What is the average electron velocity in a copper wire of diameter 10 millimeter carrying a current of 1 ampere? Assuming that each atom contributes 2 free electrons to the flow, and the molar mass of copper is given as 64 gram per mole, and the density of copper is 9 gram per centimeter cube. Now to calculate the electron velocity, you need to first calculate the free charge density rho. Charge density is charge per volume, which you can write as charge per atom multiplied by atom per mole multiplied by mole per gram multiplied by gram per volume. So atom cancel, mole cancel, gram cancel. You have charge per volume, which is your charge density. Charge per atom. I said each atom contributes 2 free electrons. So 2 multiplied by charge of 1 electron, 1.6 into 10 to the power minus 19 coulomb. Now 1 mole contains Avogadro number of atoms. So atom per mole is 6.023 into 10 to the power 23. Now mole per gram. So we know it is 64 gram per mole. So mole per gram is 1 by 64 multiplied by gram per volume. This is density, which is 9. So this gives you 2.8 into 10 to the power 4 coulomb per centimeter cube. We know the definition of current density. This is current per unit area perpendicular to the flow, which also can be written as charge density multiplied by velocity. From this, we know velocity equal to current divided by pi r square, which is a cross-sectional area multiplied by charge density rho. And if you plug in the values, this is 10 to the power minus 2, sorry for the typo here, you get this is equal to 0.0045 centimeter per second. In 1 second, electron moves only this much distance. So this is the reason why I assume that velocity is almost 0 in this derivation. So you may be still wondering, if the velocity is very low, then how are we seeing an instant response when you put on the circuit? So we'll come to that later. Before that, let's do one more problem. A cylindrical resistor of cross-sectional area A and length L is made from a material with conductivity sigma. If we stipulate that the potential is a constant over each end and the potential difference between the ends is V, what current flows through the wire? Now in this case, the electric field is uniform for a conducting wire. I will show that very shortly. And the conductivity is also uniform throughout the material. Now from the definition of current density, I can write current I equal to current density J multiplied by area. J can be written as sigma multiplied by E. Now electric field I can write in terms of the potential difference. It's a gradient of the potential. In this case it is potential divided by total length. So current equal to sigma A by L multiplied by V. Let's have a closer look at this term sigma A by L, or take the inverse of that, L by sigma A. So 1 by sigma is resistivity, whose unit is ohm meter. Then you have L by A. So this is meter per meter square, which gives you 1 by meter. So you have ohm meter divided by meter, which gives you the unit of ohm, which is nothing but resistance. So this term L by sigma A is resistance R. So I equal to V by R, or V equal to IR. So this is a more familiar version of Ohm's law. So you can derive this version of Ohm's law from this fundamental version. Now if you assume that the current flowing through the conducting wire is a steady current and conductivity is uniform throughout the material, then a divergence of E you can write in terms of the current density as divergence of J divided by conductivity sigma. Since we are talking about steady currents, divergence of J equal to 0. From the Gauss law, we know that a divergence of E equal to rho by epsilon naught. Epsilon naught is a constant, so the only possibility is the charge density rho being 0. So charge density inside the material is 0 and any unbalanced charge resides on the surface. If you recollect the story from electrostatics, we have derived the same result in the case of conductors. For conductors, field inside the conductor is 0. Consequently, the net charge density inside the conductor is 0 and any unbalanced charge resides on the surface. So whether it is a stationary charge in a material or a moving charge in a material, the results are pretty similar. When I say charge density is 0, it doesn't mean that there is no charge inside the material. It's just that there is equal amount of positive and negative charges, and the net charge density becomes 0. Now, if you take this equation J equal to sigma E or E equal to J by sigma, in the case of a perfect conductor, sigma is infinity, so you get electric field E equal to 0. Meaning, even without any push, since the conductivity is very high, without giving any significant amount of push, the charge is able to flow through the material. That is why when we connect circuit components using conducting wires, usually we treat those wires as equipotential component, because the field is 0, almost 0, and the potential is constant throughout the material. On the other hand, resistors are made of poorly conducting material, so you need to provide a significant amount of push to make charges flow through the material. Consequently, the potentials are not same on the ends of the resistor. It always flows from the end of higher potential towards the end of lower potential. Now let's go back to our previous example of switching on a bulb. The moment you switch on the circuit, you see the bulb glow. Now we have a couple of questions here. First one, the bulb is connected to a battery. So battery provides a potential difference, or you can view it as a force from the battery. So obviously we are providing force from the battery. So close to the battery, force is high, and as you move away from the battery, the force decreases. So naturally you expect a higher current close to the battery, and as you move away from the battery, the current decreases. But if you take a multimeter and measure the current at any point in the circuit, you will find that current is the same. So how does this happen? Also, we need to answer our previous question. We know that the velocity of charge in the circuit is very, very low. Still, moment you switch on this circuit, you see that the bulb is glowing instantaneously. So how does this happen? Now, there are two forces coming into play here. First one, of course, the force associated with the battery or the source, you call this as Fs. This is confined mainly to the source. And there is a second type of force here. All throughout the material we have electric charges, and the charges have electric field associated with them. So we also have an electrostatic force E. And it is this force which smoothens out the flow and communicates the influence of the source to the distant parts of the circuit. Now, how does the electrostatic force smoothens out the flow? Suppose we have a bend in the wire, and the current flowing into the bend is more than the current flowing out from the bend. So there is a local accumulation of the charges here. As a consequence of the accumulation of charges here, a field develops which objects the current flow into the bend and promotes the current flow out of the bend. So this goes on until the current flowing in is equal to current flowing out. So the charge accumulation vanishes and the current flows uniformly through the bed. So this is a self-correcting system. And also, how does the information from the source reaches the bulb instantaneously? So when I say current flowing through the wire, don't think that the same electron is flowing through the entire wire and reaches the bulb instantaneously. No, that's not the case. We are talking about conductors here. Conductors carry an infinite number of free carriers. So you have electrons at every point on this wire. The battery provides an initial push, Fs, and this push is communicated from one charge to the other charge through the electrostatic force. So each electron carry forward this push, and since you have an infinite number of electrons throughout the circuit, this happens quite instantaneously, and within no time the information from the source reaches the bulb. So the total force in this circuit is a combination of the source force Fs plus electrostatic force E. Now the electromotive force EMF is defined as closed integral F dot dl. Since closed integral E dot dl equal to 0, you can write it as closed integral Fs dot dl. So when I say electromotive force, don't think that it is a force, it is an integral of the force. Or since F dot dl is the work done, you can view it as work done per unit charge by the source. Now if you take an ideal source with zero resistance, if you recollect the case discussed before, in the case of an ideal source, the electric field or the force on the charge is 0. So here the net force on the charge is 0 because you have infinite conductivity here. So F equal to 0, you can write E equal to minus Fs. Now the potential difference between the two terminals A and B of the battery you can write as B equal to negative integral A to B E dot dl, or instead of minus E you can write plus Fs. So this is integral A to B Fs dot dl. We have defined this integral between terminals A and B, but you can also extend this integral to the entire circuit. Since Fs is confined only to the battery, when you extend this integral, the value of the integral is not going to change. So this is closed integral Fs dot dl, which is nothing but EMF. So the role of the battery here is to establish a potential difference which is equal to the electromotive force, and the electrostatic force associated with this EMF, it pushes the electron throughout the circuit. Now one device which makes use of the motional EMF is a generator, where a conducting wires moves in a constant magnetic field. So assume that you have a region of a uniform magnetic field. The direction of magnetic field is into the plane of this screen, and you have a conducting loop. So when this loop moves inside this magnetic field, a current is set up in the loop. So assume that the loop is moving towards the right with velocity v. So the sides AD, AB and BC are exposed to the magnetic field. So these sides are going to experience a magnetic force. Now let's take the side AB. The charges in the side AB are moving towards the right with velocity v. So a magnetic force QVB is set up in this side, and the direction of this magnetic force is in such a way that it drives charges in the clockwise direction. On the other hand, if you look at charges sides BC and AD, they also experience magnetic force, but in this case the force is perpendicular to this side, so they do not contribute to the current flow. Now if you estimate the electromotive force, integral F magnetic dot dl, this is equal to VBH, where h is height of the loop. I'm not going into the details of the derivation, you can find it in the textbook. So EMF equal to VBH. Now the flux through the loop is given by a magnetic field multiplied by area of the loop, Hx. Now when you move the loop through the magnetic field, the flux is going to change. So since you are moving it towards the right, flux is decreasing. So you can write the decreasing flux act d phi by dt equal to bh dx by dt. dx by dt is velocity v. So this is equal to minus bhv. The negative sign is here to indicate that flux is decreasing. But BHV is nothing but the electromotive force. So you can write electromotive force E equal to minus d phi by dt. This is known as flux rule for motional EMF. Electromotive force is negative rate of change of magnetic flux. In the year 1881, a brilliant physicist Michael Faraday did a series of experiments which became a turning point in the history of electromagnetism. In fact, it was Michael Faraday who introduced the concept of field and the line of force, and later James Clerk Maxwell, whatever ideas provided by Michael Faraday, he made it more quantitative by describing the line of force using Newtonian mechanics. So Michael Faraday did three major experiments. In the first experiment, he pulled a loop of wire to the right through a uniform magnetic field, and he observed that a current flowed through the loop. In the second experiment, he held the loop steady but moved the magnet towards the left. Again, a current flowed in the loop. In the third experiment, both the magnetic field and the loop remained stationary, but he changed the strength of the magnetic field. Once again, current flowed through the loop. In all the three cases, the magnetic flux associated with the loop changed. Consequently, an electric field developed. So Michael Faraday inferred that a changing magnetic field induces an electric field. Now, this proved to be a very, very important discovery, because up to this point, people treated electricity and magnetism as separate phenomena. But from this point onwards, people realized that these two are interconnected. So till now it was electricity and magnetism. Now onwards we can call it as electromagnetism. There is an inherent connection between these two. Now there is one fundamental difference between these two cases. I need to emphasize that. In this case, the loop is moving, the magnetic field is stationary. When the loop moves, the charges inside the loop, they move with the velocity v. So they experience a magnetic force, and this magnetic force sets up an EMF in the loop which drives the current. So inherently, the EMF we discuss here is magnetic in nature. In the second case, the loop is stationary. The charges are not moving. Since stationary charges cannot experience magnetic force, the EMF here is not set up by the magnetic force. It is set up by the electrostatic force associated with the charge. So the EMF here is electric in nature. In any case, the EMF can be written as a line integral of the force. The force here is the electrostatic force. So this is equal to closed integral E dot dl, which can be written as minus d phi by dt using the flux rule. Now, flux can be written as integral b dot dA. So closed integral E dot dl equal to minus integral dou b by dou t dA. This is the integral version of Faraday's law. Now I have a line integral on the left side, surface integral on the right side. I can convert this into the surface integral using Stokes' theorem. So this becomes curl of E into dA. So I have now surface integral on both sides. You can equate the terms inside. You get curl of E equal to minus dou B by dou T. This is the differential form of Faraday's law. Now if you compare these with the results from electrostatics, if you recollect, we have derived that closed integral E dot dl equal to 0 and curl of E equal to 0. You can make out the difference between electrostatics and electrodynamics here. So in electrodynamics, what we are trying to do is try to develop a more holistic picture, a more complete picture of the entire electromagnetic phenomenon. And as you have already noticed, electrostatics is a specific case of this grand picture. So the grand picture is slowly unveiling. There is more to come in the coming lectures. So stay tuned. See you in the next class. Thank you.